Welcome back, guys. For today's video, we're diving into the mesmerizing world of chaos game and fractals. All these patterns are a product of this method. Let's take a look into what exactly chaos game is, how it works, what it's good for, and we might discover some new fractals while we're at it. So what is chaos game exactly? Chaos game might best be known as a method of creating fractals. What's a fractal? I like to think of a fractal as a complex geometric shape that has repeating patterns within itself. We can zoom as far as we want into a fractal and still find the original pattern repeats infinitely. You may have heard of things like the Sierpinski triangle or the Mandelbrot set. These are all fractals with these same properties. A simple version of chaos game starts by randomly selecting a point inside a regular polygon, as well as a random vertex. Let's connect these points. Next, we can calculate the midpoint of these points by taking their average and making it our next point. Now all we need to do is repeat these steps several times. And by several times, I mean several thousand or million times. It goes from looking like a few meaningless dots to a beautiful fractal triangle. It's like the Sierpinski triangle we saw earlier. Now there are lots of different ways you can use these steps to generate patterns. Let's go through some of them. This method works for any regular polygon, so it'll work for triangles, squares, pentagons, hexagons, heptagons, octagons, and beyond. You can also change the step where you select the midpoint to use Lerp instead. Here's a simple function for Lerp, also known as linear interpolation. Lerp applied to the x and y of two coordinates allows us to select any point along their connecting line. We pass a progress or percent value that tells us where in between our coordinates we want our new point to be. This value should be in between 0 and 1, let's call it r. This alone can completely transform the pattern into other interesting forms. But now we're getting at the point where we need to change mediums to drastically increase our point count and lower their size to see the more intricate changes. We've been stopping at a few thousand points. Let's up the point count to a few 100,000 or million. Man, that's so much crisper. Probably the most important dial you can adjust to create unique fractals using the chaos game method is to change how the vertices are picked. If we assign each vertex in our polygon a point number, we can use the previous vertex pick to apply logic to find the next point. The example we saw earlier picked the vertices randomly, but you can pick them using any logic you can think of. I find the more interesting patterns involve some amount of randomness, but switch to using predetermined logic to find the next vertex when certain conditions are met. For example, we could keep selecting random points, but decide to reject any vertex that is the left neighbor of the previous point. Or we could reject any vertex that neighbors the previous point at all. We could only allow visiting the previous vertex's neighbors. Or we could also disallow selecting the same vertex twice in a row. You see, adding a simple rule can have dramatic effects to the pattern produced. But what if I told you we can apply logic using more than just the previous vertex as an input? We can actually look at any of the previous vertices and use them to determine the next vertex with arbitrary rules. This opens the door to a lot more logic that can be applied to discover unique fractal patterns. Here's what you get when you select vertices in a 1-2-1-2 pattern. And here's the result if you pick vertices in sandwiches. Here's some triple sandwiches. And here's what you get when you disallow neighboring vertices, but only when the last two randomly selected points are the same. Another input I experimented with is the iteration number. Using this as an input, you can create hybrid rule sets that create stunning patterns. While some of these might not be strictly fractals, they're definitely cool to look at. There's really no limit to the number of rules you can apply to generate unique fractals. Don't believe me? We'll take a look at this rule. I named it clockwise 3 triple sandwich, counterclockwise 2 no neighbors, 2 clockwise 4 no opposite, 2 counterclockwise 1. Don't worry about that weird naming convention, I can break it down for you. This is a chain of 19 rules executed in order using the modulo of the iteration number. We travel clockwise for 3 points. Then we create a triple sandwich, which is just a term I use for a sequence of numbers in this order. These points fill up the next 5 spots in our sequence. Next we travel counterclockwise for 2 steps. We then randomly select a vertex twice, excluding neighbors. Then we go clockwise again for 4 steps. The next 2 steps, select random vertices, excluding the vertices opposite of the previous one. Then finally we travel counterclockwise once for the final step. Repeat this enough times and you get this crazy looking pattern. This rule set doesn't even use heavy if-then logic, just simple logic for 19 steps. Imagine a rule with 100 steps, not to mention other rules that could be made using trig functions or other math jazz. This leads me to believe that it's probably possible to inscribe any symmetric pattern using just about any set of shapes. That would probably take an absurd amount of trial and error for some of them, so maybe it's a task to send off to AI or genetic algorithm. As I'm sure you can tell, I spent plenty of time coming up with different rule sets to get unique patterns, and I could have spent a lot more time and never run out of vertex selection logic ideas, but there's only so much I can fit in this section. Let me know in the comments if you guys came up with any other patterns. I'd love to see them. So we know how to use Chaos Game to generate patterns with random numbers or rule sets, but we can also generate patterns using predetermined sequences. For example, here's what you get when you map all the prime numbers up to 10,000 to the sides of an octagon. I also tried the collat sequence, which has this cool attractor-like movement. And here's the Fibonacci sequence. Okay, but what is Chaos Game good for besides creating pretty patterns? I mean, they're nice to look at, but that doesn't really solve any problems. Well, Chaos Game has been found to be an excellent visual indicator of the effectiveness of a random number generator. You can tell how good it is by how many patterns appear in the visualization. We just touched on the ability to visualize arbitrary sequences using Chaos Game, and it turns out this property is incredibly useful in fields such as bioinformatics. For example, you can take a biological sequence, DNA, which is essentially a data set of nucleotides, map them to the vertices of a square, and run the same steps to visualize an entire genome. This gives a nice image of a species that's a little easier to parse than a long chain of GCAT, to say the least. Here's what a chunk of cat DNA looks like in Chaos Game representation. You can even pass this genome image to a machine learning model to find further patterns or differences between organisms that would otherwise be difficult to detect. For example, Chaos Game representation was used to answer questions about the COVID virus during the outbreak. But that really covers the main points I had for this vid. I plan on uploading a montage of the rest of the patterns I found soon, so please subscribe if you want to see that. Thanks for watching.